PLEAK is a web application for BPMN modeling focused on privacy leakage detection. Our goal is to pinpoint the data disclosures that occur in a process to assist the process designer in detecting undesired leakages. PLEAK is built on top of the BPMN.js library and contains separate components to manage the model files, create BPMN models, and several privacy-related editors. These editors are the focus of this demo. This demo is based on a running scenario that involves cargo ships and a nation with ports for the ships to dock at. The ship needs to find berths available before its deadline. The data object reachable ports contains ports that can be reached within the deadline. Feasible ports narrows this down to ports that the ship can actually fit to. The final output of the process gives the actual port and berth slot assignment for each ship. The first editor you see here is the Privacy Enhanced BPMN editor. Privacy Enhanced BPMN is a BPMN extension that captures the use of privacy-enhancing technologies in a model. It adds notations to specify the technology and its concrete operation within a classical BPMN model. The PE-BPMN editor enables the addition of PE-BPMN notation to a standard BPMN model. Clicking Select Task on a model element opens the stereotype menu. This menu is organized based on privacy goals. Choosing a stereotype, like Secure Multi-Party Computation, opens a stereotype-specific panel to add required parameters. Secure multi-party computation methods allow participants to collaboratively compute on their data while only revealing the computation output. For our scenario, tasks with the MPC stereotype are grouped based on which tasks correspond to a joint computation. The editor highlights the selected model element and other objects on the model related to the chosen stereotype. For example, other group members for MPC. The correctness of PE-BPMN models can be checked using the Validate button. An error list is displayed in case there are any problems in the model. Clicking on the error helps to locate the affected model elements. For example, the distributed nature of MPC tasks requires that there is at least 2 tasks in a group. The model can then be corrected. A valid model can be analyzed to detect potential leakages. The simple disclosure report visualizes which participants have access to which data in the process. In addition, it distinguishes between data objects that are visible or hidden. For example, the nation sees its inputs such as port, berth, and slot, and also learns the intermediate values, namely feasible ports and the output assignment. However, the nation does not have direct access to the inputs of the ship manager nor the reachable ports computed for the ship manager. PE-BPMN can also be used to summarize data dependencies. A data dependency matrix describes the interdependence of data objects. However, PLEAK offers more means to go into details of the dependencies. Next, we present the leaks when analyzer as part of the SQL editor. PLEAK's leaks when analysis takes what we call an SQL workflow as an input. This input is simply a BPMN model where each task corresponds to SQL scripts that manipulate input database tables and produce temporary tables. For example, the task Select Reachable Ports takes the tables port, ship, and parameters as inputs and produces the table Reachable Ports. Using PLEAK's SQL Privacy Editor, one can add SQL scripts to the BPMN model. For instance, for the table port, one would enter an SQL create table statement using the SQL editor provided in PLEAK. The same has to be done for the table ship and other input data objects. The data object marked parameters here is a special table that we use to define the name and data types of the input parameters for the overall computation. In this scenario, we assume that the SQL workflow is executed for one ship at a time, such that the input would be the ship's name. In addition to the name, a deadline for the arrival of the ship is needed as input. As mentioned before, the SQL script specified within task select feasible ports takes the tables defined by the port, ship, and parameters as input and selects the set of ports that the ship can reach before the deadline. The SQL script required for this purpose is not trivial and is defined with 2 stored procedures and 1 select statement. It is worth noting that PLEAK's leaks when analyzer can process PostgreSQL's SQL dialect. In particular, in this example, there is a store procedure that uses an extension of PostgreSQL that computes the distance over the Earth's surface given the coordinates of 2 objects. Once the entire BPMN model has been annotated with SQL, the analyst has to select one or more output data objects and then start the leaks when analysis by clicking the button Leaks When Report. At this moment, PLEAK collects SQL scripts for each of the runs of the BPMN model and sends them to the backend for its analysis. At the end, PLEAK will show the Leaks When report for each column of the output tables. For example, we can see that the reachable ports data object has 2 columns, port and deadline. The Leaks When report shows that the port ID is disclosed if the ship can reach the port by a given deadline. The deadline is computed from its speed and distance from the port as determined from its coordinates. The second column in the reachable ports table leaks the arrival time under the same conditions. At the final node, each Leaks When report has 2 branches, one for the data that is disclosed and the other for the leakage conditions. The feasible ports table is computed from the reachable ports data and the Leaks When report reflects this. We can see that the deadline condition is still present for the Leaks When report of feasible ports. In addition, there are new conditions specific to this SQL query to stress that the ship's draft has to be less than the harbor depth and that the port must be able to offload the cargo. From this example, we can see that the goal of the Leaks When analysis is to identify the information that is disclosed by tasks in an SQL workflow and the conditions under which it is disclosed. The analysis output combines the leakage conditions over the queries in the workflow and presents them in an accessible format. Finally, we take a look at the sensitivity analysis. Sensitivity tells us how much information the output reveals about adding or modifying a row in the input table. Knowing the workflow's sensitivity allows us to make it differentially private. PLEAK considers 2 flavors of sensitivity: global and local. Global sensitivity quantifies the magnitude of the noise that should be added to the output to make it differentially private. It can be computed based on the table schemas and the SQL workflow, similar to the Leaks When analysis. The sensitivity matrix depicts the sensitivity of tasks with respect to the input tables. As you can see in this example, the change in the output of some tasks can be infinitely large, which means that differential privacy cannot be achieved. On the other hand, 1-row modifications to berth or slot tables can only affect at most 1 row of the slot assignment and have no effect on the intermediate results. The local sensitivity analyzer is accessible from the SQL derivative sensitivity editor in PLEAK. In addition to SQL scripts, this editor requires the user to insert actual data tables to specify the data objects. If the actual table data is available, then computing local sensitivity is useful, as it achieves the same level of differential privacy as global sensitivity, but with less noise. In addition, local sensitivity is more detailed, as the user may choose particular rows and columns to be considered sensitive. In this example, we assume that the columns offload capacity, offload time, and harbor depth are sensitive in all rows. it is possible to define more sophisticated sensitive components. In the table ship, only the third and the sixth table rows are considered sensitive. We combine latitude and longitude to define Euclidean distance from the port. We may also assign different privacy weights to different columns. Before running the analysis, we set parameters to define the privacy level that we want to achieve. The variable epsilon comes directly from the definition of differential privacy. Simply put, a smaller epsilon means more privacy. The variable beta is a parameter that can be optimized. In general, it gives less noise if it is smaller, but if it is too small, then achieving differential privacy may be impossible. Similar to global sensitivity, local sensitivity is computed with respect to each input table. The most important output quantifies the noise that has to be added to achieve differential privacy for all the input tables at once. Observing the relative error, we can estimate whether the noise is reasonable. To protect only some particular table, we may need to add much less noise and get a smaller error. To summarize, PLEAK is a tool that enables 3 privacy analysis perspectives. Privacy-enhanced BPMN tells us whether a specific cryptographic mechanism protects a data object in a process at a Boolean level. The leaks-when analysis provides a qualitative description of the data dependencies, while sensitivity analyzers quantify the information flow.